Have you ever wondered how we humans can detect objects which are flexible? Specifically, other humans. We can detect them at any different pose. They might be doing yoga, they might be sleeping, they might be walking, but we can easily detect them despite them wearing different kind of clothes, having different kind of postures. How do we actually do that? What do we need to give computers the superpower to actually enable them to do the same thing, especially for self-driving cars? In today's episode, we will talk about HoG features and we will demystify them. Let's look at a simple example. This is a video from a self-driving car. When you are driving a self-driving car, you might be looking at other people, detecting them, looking at their emotion, looking at their intent, and you might be thinking, hey, what are they doing? How fast are they walking? Things like that. A self-driving car essentially needs to do something very similar so that it can predict where the people are going to be, so that it doesn't abruptly brake in front of them, and it actually seems natural and intuitive to the other people when they're around these cars. Let's look at two specific examples. We have a person here with a box which is walking, and we have another person in a completely different pose, and we have a person on a bike, and then we have another person in a completely different pose which is tilted backwards. So you might be wondering, I can do something very simple like face correlation, wherein I can have a bunch of these templates, as we would call, and I could have people at different poses and just detect them, right? So let's have a look at the face correlation. If you don't remember face correlation, I would urge you to go back and look at the video on filtering in the frequency domain. It's a beautiful video. Please go watch it, and I think this will be very intuitive after you have watched that. So we can take the magnitude and the angle spectrum or the phase spectrum of both of these people, and just matching the magnitude doesn't really help, as it doesn't really add much value. So we can look at the phase values and we can essentially take the histograms of these phase values, right? Let's have a look, and this is what it looks like. And you might be like, if you squint hard enough, you might be like, oh yeah, this looks very similar. I can easily detect these two people as the same thing. But the question is, if I bring in the spectrogram of a car, it also looks similar, right? So if we are just looking at global gradients, there might be poses where the human might look like a car, and the control policy which the autonomous driving robot or you as a human being would take if it's a car versus a human is very different, right? And you don't want to do that. So what can we do, right? As in computer vision, we have seen this before. If we can't do something at a large global scale, we will split the image up into smaller patches and we will look at the local values of these things. So let's patch this image up into, let's say, 8x8 or 12x12 or 16x16 grids. And at each of these patches, we will basically look at a histogram of orientations, right? Let's do the same thing. And this is what it would look like. And in this particular case, the length of that line basically indicates how many values there are in that histogram, and the angle is represented by where that line is tilted, right? And you can clearly see that there are certain parts which are like dominant in direction, certain parts which are more uniform and flat, and there are certain other parts which are dominant in the other direction. So what we will do is we will essentially patch the image up. For each of the patches, we can do something like a simple Sobel operator in X and Y, or we can do like a Fourier spectra and take the phase spectrum, and then we can basically take these orientations and bin them into like 4 or 8 or 12 or 16 values, and this is called the orientation binning. So the actual value of the number of things doesn't matter as much. So what we will do is we will normalize this histogram, and once we normalize this histogram, we want to basically make a feature vector out of it. So we will use an operation called vectorization, wherein we take all these values, put it in a vector form, and we will call that as a feature vector or the feature descriptor for that particular patch. This exact concept is called the histogram of oriented gradients or HoG operator. So now let's look at the person along with the other person. And if we apply the HoG features, this is what it looks like. It's actually really hard to see that they're similar or dissimilar. Let's do the same thing for a car. Again, it's really hard to see. If you squint really hard, you might be able to say that, hey, like the one in the car is a little shifted, it doesn't look the same, but the one on the person is closer. A mathematical operation to do this would be to take something like an L2 distance. And if you take the L2 distance, you will see that the HoG feature descriptors of the two people, despite them being at very different poses and different amount of occlusion levels, are actually much lower. It's about 470.5 versus 551.1, right? Great. So this means that the lower value here is a better match. Beautiful. So we constructed a HoG feature which is based on the local orientations, and we are able to actually detect people from different poses, and like we can differentiate and distinguish them from a car. The question is, can we utilize this for detection of faces, right? So let's look at this image wherein we have Leonardo DiCaprio's face, and we are going to use this nominal frontal face image to detect people in this image. Okay. So what we will do is we will basically obtain the HoG features on both the images, and we will basically do a simple L2 distance, and we will retain all the centers and the sizes of the HoG features which had a good match over certain thing, right? But you'll see that there are multiple face hits we are getting across these faces, and we want to reduce this. So we will basically utilize something called the intersection of union test. The idea is that you have two bounding boxes and you look at the amount of intersection area they have to that of the union area, the total area they cover. And you take this ratio. If the ratio is greater than some threshold, you will basically only retain one of the bounding boxes as they refer to the same object entity. Okay, and this is called the non-maximum suppression, which is great. So let's find the maximum score bounding box, right? And then let's remove the bounding boxes which have an intersection over union or commonality greater than 50%. You keep repeating this for like the next highest bounding box score and so on and so forth. And with this, you should in theory be left with only two bounding boxes. We only have two faces here, but because no algorithm is perfect, we will actually be left with three bounding boxes. And the number on the top of the bounding boxes tell you the overall confidence. But remember that we started this story with that, hey, humans are flexible. How do we do that, right? Even with the previous example, if you maintain a particular like histogram of oriented gradient filter for each of the poses, it is too many, right? It's too difficult and too hard. Instead, what we can do is we can have this thing called a root filter. In the root filter, what we can do is we can say, hey, we know that the head is in this general area, the hands are in this general area, the legs are in this general area, and so on. If you remember the geometric features video, this is exactly what I'm talking about. If you do not remember that, I would highly urge you to go check that out now, because the concept is exactly the same here. We say that the body parts are almost always relatively oriented in a particular way, and we are going to weigh or model these as like weights of a spring, or in other words, like a penalty function if it's too far away from that. Okay? And this is what it would look like. This paper is called the Discriminative Parts Model, or DPM, and it's one of the most pivotal works in the field of computer vision for working with flexible objects. Okay? This was a paper by Ross Gershik, who is one of the founders of the Region Convolution Neural Network, which we'll talk about in one of the future episodes, and he was working at Facebook Research. And then we have Pedro Falzenswab, who worked extensively on graph-based segmentation at Brown University. And then we have Devaramanan, who is basically the person behind the Microsoft Cocoa dataset, founded the Argo AI, and was a professor at Carnegie Mellon University. So in 2012, there was this challenge called the Visual Object Classes Challenge, where the goal was to detect objects from multiple varying classes. And this was one of the state-of-the-art challenges wherein like it would push the boundaries of every single algorithm, handcrafted or otherwise, right? And the discriminative part model was one of the main models which was used as a benchmark in this. And this is, even to this day, it turns out to be one of the classical models which actually works very well despite relatively low computational cost. So I would urge you to check that out. Just to quickly recap, what is a HoG feature? How can you detect faces with HoG features? What is the algorithmic steps? and what changes do you need to make to these HoG features, or what additional properties do you need to impart to make it work for flexible objects. See you next time. Take care. Bye-bye.